Recently, I installed a CP22E antenna, which is a stacked 2-element 5x8 lambda vertical antenna with a facing coil in between. 5x8 lambda vertical antenna has a length a little more than the usual quarter wave length vertical antenna. It has a similar low angle of radiation useful for local contacts. Hence, it is a popular form of mobile antenna which can be mounted on a car. Mounting can be with a magnetic base so that it avoids drilling the car chassis, with obvious advantages when you consider resale of the car. Matching coil is provided at the base of the antenna to give good impedance matching like that of a 3/4 lambda vertical antenna. Under ideal conditions, 5x8 lambda vertical antenna has a 4 dB gain over a quarter wave vertical antenna. When it is mounted on the car body acts as the ground plane. 5x8 lambda vertical antenna mounted on a car is typically used for VHF and UHF amateur radios. It can be used as an HF antenna for a base station as well. In that case, the low angle of radiation will be useful for DX contacts. My Twitter friend Jim Reed and 4BFR is using a Discone antenna to receive amateur radio signals from International Space Station. Discone antenna, as the name implies, is a combination of a disc and a cone, typically mounted vertically with the disc on top and cone below it. Discone antenna is vertically polarized and has gain similar to a dipole, but the specialty is that it is exceptionally wide band with a frequency range ratio of about 10:1. One such antenna made of solid copper sheets can theoretically cover from 700 MHz to 2 GHz. Instead of solid metal sheets, metal wires or rods in spoke configuration can be used to approximate a solid surface at lower frequencies. This reduces the risk of damage to the antenna by wind. Discone antenna has a narrow radiation pattern in the vertical plane with highest sensitivity in the direction of the horizon. As expected, it is less efficient when employed as a transmitting antenna than an antenna designed for limited frequency range. The disc diameter is 0.7 times a quarter wavelength of the lowest frequency expected. Feed point is at the center of the disc into the central conductor of a 50 ohms coaxial cable. Outer conductor of the cable is connected to the cone. Length of the cone should be a quarter wavelength of the lowest operating frequency. Cone angle is between 25 to 40 degrees. Cone and disc are separated by an insulator. Full wave loop antenna is also known as self-resonant loop antenna and large loop antenna. Other loop antennas are halo antenna and small loop antenna. Perimeter of the full wave loop antenna is slightly more than a full wavelength of the operating frequency. It is quite efficient and can be used for transmission and reception. Small loop antenna is mostly used as a receiving antenna. Shape of the loop can be a circle, triangle, square, rectangle, or any closed polygon. A popular form of full wave loop antenna is quad antenna with a square shape constructed with a wire strung on an X-shaped supporting frame. Additional parasitic elements can be used as director and reflector. Such an antenna array will have unidirectional gain which increases with each additional parasitic element like a Yagi-Uda antenna. The antenna gets a diamond shape if mounted on a plus-shaped support. A triangular full-wave loop antenna is another form of a vertical loop which requires only one elevated support. In a special case of full-wave loop antenna, a rectangle which is twice as high as its width gives a better gain and can match 50 ohms directly if used as a single element. Different shapes of loop antennas will have different gains and impedances. Gain and impedance also changes with the location of the feed point on the loop. My Twitter contact G6AD uses a full wave loop of wire at 30 feet for 80 meters. It is coax fed to a 2:1 transformer. With that setup, he is able to work DX on 80 meter with 100 watts. Bazooka antenna is a coaxial dipole antenna with the main part made of coaxial cable. It was originally designed by the staff at Massachusetts Institute of Technology for radar use with coaxial cable for the entire radiating elements. Adaptation for ham radio uses coaxial cable only for the broadbanding portion, while ladder line is used for the rest of the antenna. Bazooka antenna is a single band antenna with a broad bandwidth within the band, unlike the dipole which has only a bandwidth up to 100 kHz. Moreover, Bazooka antenna does not radiate harmonics of the operating frequency and feed line radiation is very little. Bazooka antenna modified for ham radio uses does not need a matching balun and can be directly connected with 50 ohm coax. As the antenna has no exposed metal wire, static charges do not build up and reduces noise compared to exposed wire antennas. Bazooka antenna consists of a half wavelength coaxial line with outer conductor cut at the center and the feed line connected to the cut ends of the outer conductor. Inner conductor is not cut and does not radiate. It acts as a quarter wave shorted stub and serves to increase the bandwidth by cancelling reactance at off resonant frequencies. Central conductor and shield of the antenna element coax are soldered together at both ends, shorted. Two wires of the ladder lines are soldered to this joint on both sides of the coaxial antenna elements. The other ends of the ladder lines are also shorted by soldering the wires together. K5IJB has provided calculations of lengths of the coaxial cable segments and twin lead segments for various amateur radio bands from 40 meter to 6 meter. Several types of monopole antennas are used for radio transmissions, both amateur and professional. The tall tower antennas often seen near medium wave radio stations are monopole antennas. Unlike an amateur radio tower with a Yagi-Uda directional beam antenna at the top, the tower as such is the radiating element for such broadcast stations. Ground plane for the tower antennas of broadcast stations are formed by a set of cables buried under the ground. The tall mast radiators of broadcast stations are usually supported by multiple guy wires in several directions with insulators in between. Red beacon lights are also visible at the top if you happen to see them at night. Other aircraft warning lights are seen along the height of the mast as well. Special RF blocking devices are needed to prevent their power supply lines from conducting the high RF voltages on the antenna down to the power source. These mast radiators are quite different from the microwave towers of the telecom department and mobile phone antenna towers. Those towers have several directional antennas on top, receiving and transmitting signals in various directions, linking them with other towers at a distance as well. Interestingly, some broadcast stations may also allow co-location of antennas for other purposes on their tower. A monopole antenna which is quite familiar to the ham radio operator is the rubber ducky used on handheld radios. These are used on other types of walkie-talkies as well. It has a helical coil inside and the outer covering is made of flexible material which gives it the name. Helical nature of the wire gives added inductance to cancel out the capacitive reactance of an electrically short antenna, which is typically shorter than the quarter wavelength of the operating frequency, sometimes even just 1/10 of the operating frequency. Though the inductance of the helix matches the impedance, performance in terms of gain and range is less than the standard quarter wavelength antenna. Whip antenna, commonly seen on automobiles, are also monopole antenna with a helical wire either inside it or outside it and a flexible base material. Ground plane vertical antennas used for VHF and UHF work are also monopole antennas. Usually they are of quarter wavelength radiating elements and the ground plane is formed by 3 or 4 radials. Maximum power in horizontal direction and gain among the ground plane monopoles will be for a 5 by 8 wavelength vertical antenna useful as a mobile antenna for VHF and UHF. When it is mounted on an automobile body, the ground plane is formed by the vehicle body. Magnetic mount antennas for mobile use also come under the category of monopole antennas. They are popular among ham radio operators who do not want to drill the chassis of their vehicle to put a mobile antenna. Drilling the chassis would also affect the resale value of the vehicle. Magnetic mount antennas can also be used as indoor antennas to access a nearby VHF repeater if you can put them over a tall steel almirah which will act as a ground plane. I could use it in this way to access a repeater which was 30 kilometers away. Radiation pattern from all these monopole antennas discussed are vertically polarized. The first monopole antenna was invented by Marconi in 1895 and bears his name as Marconi antenna. In the original description, there was a metal plate at the top which was later found to be unnecessary and removed by Marconi himself. Yagi-Uda antenna is very popular in amateur radio or ham radio. It is also a common sight on house tops before the era of cable TV and satellite TV. It consists of a driven element and a variable number of parasitic elements on a boom. The driven element could be usual dipole or a folded dipole. Element behind the driven element is the reflector. Elements in front of the driven element are called directors. Typically, the reflector is longer than the driven element, while directors are progressively shorter than the driven element. Output of the radio is fed only to the driven element. Animation illustrates how a 4-element Yagi-Uda antenna works. There are 2 directors and a reflector in addition to the driven element dipole. The parasitic elements act as resonators by absorbing and re-radiating the electromagnetic waves from the driven element with a phase difference. There is constructive interference of these electromagnetic waves in the forward direction as they are in phase and destructive interference in the reverse direction as the waves are out of phase. Net effect is a stronger signal in the forward direction and a weaker signal in the reverse direction. This is usually mentioned as the forward-backward ratio of the antenna. In the animation, the signals are color-coded similar to the antenna element for ease of recognition. Yagi-Uda antenna is often called as a beam antenna in amateur radio. Due to the size, it is less often used on HF bands than on VHF and UHF bands. The number of elements practically feasible are also lower on lower bands. They are used with antenna rotators as good directional antennas. Yagi-Uda antennas can have gains up to 20 dBi and a front-to-back ratio of up to 20 dB. Radiation pattern is linearly polarized with horizontal polarization for a horizontally mounted antenna and vertical polarization for a vertically mounted one. Bandwidth of Yagi-Uda antennas is relatively narrow with a narrow range of frequencies within a band at which it has good gain and operable feed point impedance. The driven element or radiator can be a simple dipole with 2 quarter wavelength rods connected to either conductors of the feed line. In some versions, it is a folded dipole which has a higher impedance of around 280 ohms. The television antennas of yesteryears with folded dipole used to be fed using a twin lead transmission line with impedance of about 300 ohms. Folded dipole will need a matching for amateur radios with impedance of 50 ohms. Usual dipole has an impedance of around 70 ohms. Spacing between the elements may vary from quarter wavelength to 1/10 of a wavelength depending on the design. Radiation pattern of Yagi-Uda antenna is along the axis perpendicular to the plane of the elements towards the direction of the directors. As the parasitic elements have zero RF voltage at the center, they can be directly attached to the boom. But this will electrically shorten them, and usually a correction in length is needed to cover this. There are versions in which all elements are insulated from the boom as well. The two halves of the center-fed dipole have to be insulated in the location of the boom. Folded dipole antennas were a common sight on rooftops as part of Yagi-Uda television antennas in the past. Now, with cable television becoming more popular, we seldom see any folded dipole antennas on rooftops in my region. Still, folded dipole antennas as part of Yagi-Uda directional beam antennas are popular among radio amateurs who operate on VHF and UHF frequencies of the radio spectrum. Viewing from a homebrewer's aspect, it is technically more difficult to make folded dipole antennas as you have to bend the aluminum tubings usually used for such antennas at right angles twice on both sides. Hence, I am yet to venture into homebrewing of a folded dipole antenna. Folded dipole can be considered as a dipole antenna on top of which a loop of conductor is added so that it will be short-circuiting any direct current fed to the antenna, though antennas are typically fed with alternating currents. Folded dipole is a balanced antenna and has to be fed by a balanced feeder like a twin-lead ladder line. If a coaxial cable is used to feed the folded dipole antenna, a balun or balanced to unbalanced transformer has to be used. While the usual half-wave dipole antenna has an impedance of about 70 ohms, folded dipole antenna has an impedance of around 280 ohms. So it matches well with a ladder line of 300 ohms impedance. Earlier, twin-lead ribbon tapes were used to connect the folded dipole antenna to the television receiver. Folded dipole antenna has a higher bandwidth than the usual half-wave dipole antenna. There can be variants of the dipole antenna in which the additional conductor loop can have a different thickness with a change in the feed point impedance. Another implementation is adding another loop on top of the first loop so that three longitudinal regions are there for the folded dipole. Such multi-conductor folded dipoles can have an impedance of 600 ohms instead of the 300 ohms of the standard folded dipole. Bandwidth is higher for such folded dipoles. One reason for using folded dipoles instead of usual dipoles in Yagi-Uda antenna is to increase the impedance. When parasitic elements are there close by, the impedance of a standard half-wave dipole antenna may be reduced, sometimes making matching difficult. Another reason for considering folded dipole as part of Yagi-Uda antenna is to increase the bandwidth in order to cover a full amateur radio band. Radiation pattern of a folded dipole is similar to the standard half-wave dipole in a figure of 8 pattern in the E-plane. As the two conductors are near each other, the folded dipole is considered like a single conductor of half wavelength and has a directivity similar to half-wave dipole. The distance between the conductors is small compared to the wavelength of the operating frequency. There are several versions of multiband inverted L antennas out there. I thought of describing a center-fed one and an end-fed one. Center-fed one has been described by W4RNL and end-fed one by VK6YSF. A center-fed inverted L for 80 meter would be 65.5 feet tall and having a horizontal limb of 65.5 feet. Lowest end of the antenna will be 4.5 feet off the ground. As it is a complete dipole, it does not need a ground plane beneath it, unlike a quarter wave antenna. A parallel feed line of 450 or 600 ohms impedance and an antenna tuner are needed for multiband operation. The N-fed inverted L multiband antenna is a portable one and uses 7-meter squid pole, which is a lightweight telescopic fishing pole. Antenna is a simple light wire of 18.7 meter length. It has been mentioned that wire length could be changed but should avoid quarter wavelengths and multiples of quarter wavelengths of the intended bands. 1:9 voltage balun is used to feed a 50 ohms connection. A horizontal 5 meter counterpoise wire is also needed. This setup can be used by connecting to an automatic antenna tuner. J-pole antenna is a vertical omnidirectional antenna popular among ham radio operators for 2 meter and 70 centimeter operations. As it is an N-fed antenna, the feed point of the half-wave segment of the antenna will have high impedance, which has to be matched to the feed line by a shorted quarter-wave parallel transmission line stub. The point of attachment of the feeder coax is determined by sliding the connection back and forth along the stub, monitoring for the lowest SWR. J-pole antenna has a gain of about 2 dB compared to a quarter-wave ground plane antenna. The gain is slightly more on the side of the J stub compared to the opposite side. Parallel conductors of the J-pole antenna should be kept away from other conducting material by a distance of 2 to 3 times the spacing between the conductors. Best performance is obtained by having a non-conducting free space between the antenna conductors and the mounting structure. Separation between the two conductors should not be more than 2% of the wavelength. An important advantage of the J-pole is that it does not require radials or a ground plane. This reduces the wind resistance. A coil of coax at the feed point can serve as a choke to prevent radio frequency from traveling down along the feed line. All of you would have seen the dish antennas on rooftops being used for direct-to-home satellite television reception. They are parabolic reflector antennas. In amateur radio, they are used to receive and transmit signals to the Qatar Oscar 100, the only geostationary amateur radio satellite in orbit at present. History tells us that amateur radio astronomer Grote Reber built a 9-meter parabolic radio telescope antenna in his backyard in 1937. From local WhatsApp groups and QRZ.com, I can understand that many of the local ham radio operators are also amateur astronomers, though I am not sure how many of them are amateur radio astronomers. As the name implies, parabolic reflector antenna uses a parabolic reflector to direct radio waves. Many of you would be familiar with the parabolic reflectors in the torch lights. Parabolic antennas have high gain and produce very narrow beams compared to any other type of antenna. The parabolic reflector has to be much larger than the operating wavelength. Hence, it is practical only at UHF and SHF ranges so that conveniently sized reflectors can be made. Qatar Oscar 100 geostationary amateur radio satellite uplink works in UHF range and downlink in SHF range. Parabolic reflector antenna has a metal parabolic reflector and a small feed antenna suspended in front at the focal point of the parabolic reflector. Radio waves being received by the parabolic reflector are focused onto the small antenna, which receives the signal and transfers them to the radio through the feed line. During transmission, the reverse process occurs and the parabolic reflector sends out the beam of radio waves. Delta loop antenna is a full wavelength antenna in the shape of the Greek alphabet delta. The antenna forms a delta shape with limbs like an equilateral triangle. Though it can be made with base at the top, bottom or sides, practically it will be easy to have the base at the top as shown in the picture below. It will need a 4:1 balun at the feed point for impedance matching. Otherwise, the SWR, standing wave ratio, will be high. As with the half-wave dipole antenna, a delta loop antenna for 7 MHz will also function well with the odd multiple frequency of 21 MHz. On 14 MHz, the antenna impedance is high and SWR will be high. For the center of 7 MHz amateur radio band with frequency of 7.1 MHz, the length of the delta loop will be 43.14 meter. Delta loop antenna is fairly easy to construct if you can put up two strong poles. Recommended height is above 18.3 meters for a 40 meter antenna, which comes down to 4.6 meter for a 15 meter delta loop. Inverted V antenna is very popular among radio amateurs, especially the beginners, as it is very easy to put up and has a fairly good performance. As the name implies, it has an inverted V appearance, with the two limbs of the antenna forming an inverted V, with the apex at the tip of the non-conducting mast. As the horizontal dimension is lesser than that of a horizontal half-wave dipole antenna, it is useful when there are space constraints. Though theoretically the performance of a horizontal dipole and inverted V are similar, practically it can be lower for the inverted V. This is because of proximity to the ground, effect of ground conductivity, and end effects. Elevating the antenna higher above the ground can improve the performance of the inverted V, though it may not always be possible in a given location. Half-wave dipole antenna fed at the center is the commonest type of dipole antenna, and its length is almost half of the wavelength of the frequency for which it is meant. So the total length of a half-wave dipole antenna for the 40 meter amateur radio band will be almost 20 meter. The space needed for the antenna increases as you go down along the amateur radio bands. I had the opportunity to use both 40 meter and 80 meter half-wave dipole antenna earlier, but I'll have to struggle to get even a 20 meter half-wave dipole antenna up at my current location. Maximum radiation from the half-wave dipole is perpendicular to the conductor with almost zero radiation along the axis of the conductor. This would also mean that it would act as an omnidirectional antenna if installed in a vertical position. But installing half-wave dipole in a vertical position would not be easy for a lower amateur band. In my earlier days of ham radio, I used to simply tie the half-wave dipole across two tall coconut trees using plastic twisted flex threads. Threads would be tied to stones and flung up on top of palm leaves and pulled up in a pulley-like fashion. Of course, those half-wave dipoles used to sag in the center due to the weight of the connecting coaxial cable, and it would be almost a V antenna. A half-wave dipole antenna can also be used at odd multiples of its fundamental resonant frequency. Thus, a 40 meter or 7 MHz half-wave dipole can be used for 21 MHz but not for 14 MHz. It will act as a 3x2 wave dipole antenna at 21 MHz. The directional gain of a half-wave dipole antenna at the resonant frequency is about 2 dB. Ground plane vertical antenna is often used for VHF transmission in amateur radio. The vertical portion of the antenna is quarter wavelength. Usually, the ground plane is formed by 4 equally spaced radials of quarter wavelength each. Central conductor of the coaxial cable is connected to the vertical element, and the metallic sleeve of the coax is connected to the radials which form the ground plane. Another option is to have a conducting ground plane of at least quarter wavelength in radius. This can be considered for a mobile antenna mounted on top of a metallic vehicle body. It is an omnidirectional antenna which radiates equally in all directions. Feed point impedance is usually half that of a dipole, about 36 ohms. SWR will be less than 2:1 when connected with a 50 ohms coaxial cable. Fan dipole uses a group of parallel dipoles for different amateur radio bands fed from the same feeder coaxial cable so that the elements fan out from the feed point to either side. Impedance of each dipole is low at its resonant frequency and high at other frequencies. So a 40 meter dipole does not absorb much power at 20 meter. Each element to either side will have a length corresponding to the quarter wavelength of that frequency. Fan dipole can be mounted as a horizontal dipole or in an inverter V configuration if there is space constraints. The different elements should not correspond to odd multiple frequencies like 7 MHz and 21 MHz. In that case, both will have low impedance at 21 MHz. The elements of different bands need not be parallel but will need additional anchors in that case. Parallel elements do not need additional anchors but need insulators to keep them spaced. Dipoles are balanced while coaxial feeder is not. Hence, a balun is needed at the feed point to prevent the outer conductor of the coax from radiating RF power. Half-wave sloper antenna is also known simply as sloper antenna. It is useful when there is only a single vertical support and limited horizontal space, which is common in city dwellings. Typically, the slope may be 45 to 60 degrees. Lower end of the wire has to be at least 1/6 of the wavelength above the electrical ground. Sloper has a low angle radiation pattern suitable for DX communications. The outer sleeve of the coax will pick up RF radiated from the antenna and cause RF interference in equipments like computers in the radio shack. This can be prevented by winding a part of the feeder coax just before entering the shack into an RF choke. 8 turns of the coax wound on a 4-inch PVC former will serve as an RF choke, preventing the entry of signals picked up by the coax sleeve into the shack. Moxon antenna, also known as Moxon rectangle, is a 2-element single-frequency antenna named after Le Moxon. It is similar to a 2-element Yagi-Uda antenna with folded dipole elements and no directors. Slightly less than half of the rectangle is the driven element, which radiates the power. The other part, which is slightly more than half, acts as the reflector. It has modest directivity with a high front-to-back ratio. The driven element is mechanically connected to the parasitic element or reflector with an insulator. Moxon software from AC6LA can be used to calculate the dimensions of the Moxon rectangle antenna. Elements could be made of wire or aluminum tubings. The antenna is mounted with the rectangle horizontal and has gain in the direction of the feed point. If the elements are of wire, additional supports will be needed. Going through the QRZ.com pages of many amateur radio operators, I came across EFHW or end-fed half-wave antenna often. Unlike the center-fed half-wave dipole antenna, feed point is at a high voltage point of the radiating element instead of at the high current point. While the center-fed half-wave dipole resonates at odd multiples of half wavelength, EFHW operates at odd and even multiples of a half wavelength. This would mean a truly multi-band operation for the radio amateur. But EFHW has high feed point impedance of around 5000 ohms, unlike the 72 ohms of the center-fed half-wave dipole, which matches easily with the 50 ohms coaxial cable. This necessitates the use of a matching transformer for EFHW. This matching transformer is called UNUN as it matches an unbalanced antenna to an unbalanced feed line. A small counterpoise is used beyond the feed point. As the EFHW is a single wire, it is easy to set up, especially for portable operation. G5RV antenna is a multi-band amateur radio antenna designed by Louis Varney, who passed away in 2000 at the age of 89 years. Currently, the call sign is held by Mid-Sussex Amateur Radio Society for use on special occasions. Though the G5RV antenna was designed in 1946, it was published in RSGB Bulletin only in 1958. A PDF written by G5RV is available at the Mid Sussex Amateur Radio Society website. According to that article, it is a multi-band antenna with special feeder arrangement capable of efficient operation on HF bands from 3.5 to 28 MHz. The initial description was with a flat top of 102 feet length, a half-size G5RV for efficient operation from 7 to 28 MHz was also conceived. Special options for 1.8 MHz were also described. G5RV antenna was designed as a 3 lambda by 2 center-fed long wire antenna on 14 MHz. 34 feet open wire matching section functions as a 1:1 impedance transformer matching with a 50 ohms coaxial feeder. 102 feet was calculated using the formula for long wire antennas. An antenna tuner unit is useful to prevent automatic reduction of power for modern radios when the SWR is higher on other bands. A simple definition of counterpoise is a conductor or system of conductors used as a substitute for earth or ground in an antenna system. A counterpoise could be used by a radio amateur residing on a higher level of a modern residential system with no access to the actual ground. A network of horizontal wires parallel to the ground suspended above the ground under the antenna and connected to the transmitter's ground connection is an elaborate example. Counterpoise may also be used when the ground has high electrical resistance, as in dry, sandy or rocky soil. It would function as one plate of a large capacitor with the conductive layers of the earth acting as the other plate. Radio frequency currents from the transmitter can pass through this capacitor so that the counterpoise functions as a low resistance ground connection. But there should not be any closed loops in the wires of a counterpoise system. In such a case, strong fields of the antenna will induce circular currents in it and dissipate transmitter power.